Hello and welcome. In this lesson, we'll explore and learn how to use implicit differentiation in finding the derivative of an equation. As the name implies it, implicit differentiation is used in differentiating implicit equations. And this is a special case of the chain rule. In order to better understand implicit differentiation, we need to take a closer look at two types of differentiation: explicit and implicit. Explicit differentiation is used in differentiating explicit equations. These are the normal equations where a function f of x depends on one independent variable. As an example, I brought in f of x, and as you can see in here, f of x depends only on x, which is its only independent variable. If you were to differentiate this, and I'm going to differentiate this in two ways using prime and Leibniz notation, then I will say that f prime x equals just the power rule, 15x to the power of 1 less than 5, 4, minus 4x 1 power less than 2, which is 1, minus 7. In Leibniz notation, we'll say that ddx of the function f of x, so the derivative of f of x, equals ddx, so the derivative of 3x to the power of 5 minus 2x squared minus 7x plus 4. I want to bring your attention here to the variable in the equation of the function or expression that represents the function, and the variable in the derivative. So this indicates that we are differentiating in terms of x. And the only variable we see in the equation of the function is x. We say that the function and the independent variable in the derivative are related explicitly. So in this case, what we do to differentiate is simply use the power rule the normal way, just like we did in the prime notation. So we'll say that this would be 15x to the power of 4 minus 4x minus 7. In implicit differentiation, which is used in differentiating both functions and non-functions, equations are expressed in implicit form. What does that mean? Implicit equations are expressed in terms of not just one, but two variables. Most often, variables x and y. Sometimes, implicit equations can be transformed to be expressed in explicit form, but not all the time, as it becomes quite a long process, an elaborate process to solve an equation for y. As an example here, I brought the equation of the circle x squared plus y squared equals 25, and we will try to differentiate this in two different ways, explicitly and implicitly. If you want to differentiate this in the explicit form, then the equation x squared plus y squared equals 25 must first be written in explicit form, which means that we have to solve for y. So that means that we have y squared now equals 25 minus x squared, which will tell us that y equals plus or minus the square root of 25 minus x to the power of 2. As you can see here, we obtained two different equations. Y equals positive square root of 25 minus x squared, and y equals negative square root of 25 minus x squared. And in power form, we'll write them as 25 minus x squared to the power of 1 over 2, and negative 25 minus x squared to the power of 1 over 2. In order to differentiate x squared plus y squared equals 25, now we'll have to differentiate the two different equations that we obtained from solving for y. So we'll say that dy dx for the first equation will be ddx of 25 minus x squared to the power of 1 over 2. As you can see, this derivative is expressed in explicit form because you see that the function is expressed in terms of the same variable as the variable in the derivative. And the derivative of it would equal 1 over 2, 25 minus x squared to the power of 1 over 2, take away 1, times the derivative of the inside, which is negative 2x. As you can see here, we can simplify 2 with 2. And in a more simplified form, here we'll obtain negative x, 25 minus x squared to the power of negative 1 over 2. On the other hand, we have to continue in the same way or proceed in the same way with the second equation we obtained from this equation of a circle. And we'll say that dy dx equals, let's define the territories here. So we have negative 1 or ddx of negative 25 minus x squared to the power of 1 over 2. So again, as you can see, this is explicit differentiation, the variables match. So this would equal negative 1 over 2, 25 minus x squared to the power of 1 over 2 minus 1 times the derivative of the inside function. This is your inside function. We have a chain, negative 2x. Now remember that this negative in here will be reflected by this one. So here we go again. Let's simplify. And we'll say that the other derivative would be negative, and negative will make a positive. So these two negatives will make a positive. The 2's will simplify to 1. And then we have x 25 minus x squared to the power of negative 1 over 2. Now, as you can see, in some cases, we can actually convert an implicit equation, and there is a connection between implicit and explicit equations. And sometimes we'll be able to solve the equation or convert an equation from implicit to explicit form. However, in most cases, this will be quite a complicated process as we deal with more and more evolved equations. So implicit differentiation becomes a must. So let's take a look then at how to differentiate the same function here by using implicit differentiation and see which one we prefer. So again, we are looking at the same equation, x squared plus y squared equals 25. This is how implicit differentiation is done. So we take the derivative of each side of the equation in terms of x. So we say ddx of x squared plus y squared equals ddx of 25. Now, you know that one of the properties of derivatives states that the derivative of the sum equals the sum of the derivatives. So that means we will have ddx of x squared and ddx of y squared equals ddx of 25. And by now we have realized already that the derivative of 25 is simply 0 because it's the derivative of a constant. Now, let's start differentiating. Notice how here the variable in the function or the term we are differentiating is the same as the variable in the derivative. That's an explicit differentiation for this term. So the derivative will be 2x plus. Now notice that the variable in the function is different than the variable in the derivative. Now, we imply, and this is where the term implicit comes from, that y is some function dependent on x. So we imply that there is a chain in here, but we don't know for sure what the equation of y is or how y depends on x. And that's what the word imply means in English. So imply is something that is vaguely defined. So we know it exists, but it's not defined yet. So we know that y is some function dependent on x, but we don't know exactly how y relates to x. So when we differentiate this, and here comes to play the chain rule, we look at y as an inside function and y squared as, something squared to the outside function. So that means we have to differentiate y squared, which would be, based on the power rule, 2y. But because we know that y must be, or we imply that y must be some function dependent on x, then we have to also write or multiply it by dy dx equals 0. And if we saw the connection, or if this explanation made sense, that's all there is about implicit differentiation, okay? So there is a chain, okay, where we have an outside function. The outside function will be something squared, and the inside function, y, is a function that hasn't been defined yet, but we imply that is dependent on x in some ways. So remember that our job is to determine dy dx, which means that we have to isolate dy dx. Now, dy dx is connected, right, with the factor 2y, so they are one term here. So we're going to rewrite this as 2y dy dx equals negative 2x. So take 2x to the other side of the equation. And now we are isolating dy dx. And we do this just like we normally do in any equation. So we divide both sides of the equation by 2y. And that would equal, as you can see in here, negative 2 and positive 2 simplify to leave us with negative x over y. And this will be the derivative dy dx for the function x squared plus y squared equals 25. Now, you probably noticed that when we differentiate an implicit equation, we won't always get just x, but we are going to get the other variable, so the variable y in it, okay? But I'm going to take this one step at a time. For now, let's just practice some more examples of implicit differentiations in some similar examples as the one that we just looked at. So let's take a look at x squared plus y squared equals 100. So very similar to what we just did, but this time we also want to look at finding the value of the derivative, because we need to find the slope of the tangent at this point, just the slope. So we are going to say that if I want to find the slope of the tangent, that means that I have to find dy dx. And where do you want to draw the tangent? We want to draw the tangent at 6 and 8. In other words, we need to evaluate dy dx at x equals 6, y equals 8. So let's get to work. To find dy dx, we must differentiate x squared plus y squared equals 100. So we'll say d dx of x squared plus d dx of y squared equals d dx of 100. So This is an explicit differentiation because the variable of the term matches the variable in the derivative. So that's 2x plus. This is implicit differentiation. So the variable of the term does not match the variable in the derivative, but we imply that somehow this is some function that depends on x again. So that would be 2y, so multiplied by the derivative of the inside, dy dx. And that would equal 1 ddx of 100, which is the derivative of a constant, which we already know is 0. So we are solving for dy dx. So we want to isolate it. So then we'll write 2y dy dx equals negative 2x. Divide both sides by 2y, and then we get dy dx equals negative x over y. So we're very close to finding the slope of the tangent. So we'll make the statement that we are about to find the slope, and the slope of the tangent would equal the derivative of this function evaluated at, and careful here, so when we find the slope of the tangent, we're going to need not just one but two values, x equals 6 and y equals 8. So we write them down at the bottom of this fancy little line, and we'll say that that would be equal to negative x equals 6, y equals 8. In a more simplified form, we're going to say that this would equal negative 3 over 4. So this would be the answer to this question. Voila. Now, I brought in another example, and this is your turn to try. I will continue, but I encourage you to stop the video and try this on your own. Again, we are finding, the question is the same, the slope of the tangent to the circle x squared plus y squared equals 25. Okay, so remember that we just did the implicit differentiation of it. Okay, and we have x squared plus y squared equals 25. Nothing wrong with trying this one more time. That would be ddx of x squared plus ddx of y squared equals ddx of 25. Okay, so that would be 2x plus 2y dy dx equals 0. 2y dy dx equals negative 2x, which will make dy dx equal to negative x over y. Now you've probably already noticed that when it comes to the equation of a circle, the slope of the tangent is found the same way. If you think about it, the reason why we get the same relationship for the slope of the tangent at any point is because this is a very symmetrical shape. So I'm going to say that the slope would equal dy dx, and it's the same equation, right, that we are differentiating, and it doesn't matter, it won't matter on how big the circle is, okay, because the radius of the circle just determines the size but not the shape of it. Okay, so that's why we always obtain the same expression for the derivative. So here we go, x equals negative 4, y equals 3. That means that we have negative 4 in the numerator, 3 in the denominator, so the slope must be 4 over 3. Okay, done. All right, moving on to another example very similar to what we just did, but this time we brought x and y to the power of 3, and we want to find the equation of the tangent this time. So we're going to take the question a little bit further, so not just finding the slope but the tangent as well, which means that to find the equation of the tangent, we're going to find something in the form, or we're going to have to determine something in the form y equals mx plus b. Remember, we're going to need two things, a slope the slope and a point. The slope will be dy dx, and the x and the y coordinates are given here. So x equals 2 and y equals 1. So let's get started with finding the slope. So we write the equation as is first. And now we are ddxing every term. So ddx of 9. Okay, now again, explicit 3x squared. Implicit, because we imply again, I keep repeating it so it gets in your head. So we imply that y is a function dependent on x. So we differentiate the outside function first, 3y squared, and then we multiply by the derivative of the inside because y depends on x. We just don't know the equation of y, and that equals 0. So 3y squared dy dx equals negative 3x squared. Divide both sides by the coefficient of dy dx, and we obtain as a derivative negative x squared divided by y squared. So we'll say that the slope of the tangent will be measured by the value of dy dx at x equals 2, y equals 1. In our case is negative 2 squared over 1 squared, negative 4. Therefore, we're going to say that the equation y equals mx plus b will be 1 equals negative 4 times 2 plus b. We need to find b. So that would be equal to 1 plus 8 equals b. So b equals 9. Remember? Negative 8 take to the other side. So therefore, the equation of the tangent drawn at x equals 2, y equals 1 will be y equals negative 4x plus 9. And this would be the answer. Now, as we mentioned, implicit differentiation, we're going to do a summary of all we've said so far because we are moving on to some more challenging implicit equations. So remember that implicit differentiation is simply a form of the chain rule. And recall that the chain rule is used in differentiating composite functions where both the inside and the outside functions depend on the variable x. So if y equals f of gx is a composite function, where f of x is the outside and g of x is the inside function, we said that the derivative of y equals f of gx, so dy dx, would equal the derivative of f times the derivative of the inside. But we know that both functions, f and g, will be dependent on x. Now, the only difference with implicit differentiation is that we don't know exactly what gx is. We know that it's represented by y that is dependent on x, but we don't know exactly what the y is. So you can think of the function here as having a y, or the derivative as having a y in here, okay? So that's the only difference between differentiating implicitly and the chain rule. So in the chain rule, we know exactly what the equation of the inside is. In implicit equations, we don't. So most often, the terms that we encounter in implicit equations would be in the form d dx of y to some power, which equals n y to the power of n minus 1, and all we have to do is remember that we have to multiply by dy dx at the end. I hope this makes the process easier for you to remember, and I hope that you see the connections between them. Okay? We're moving on to some more interesting equations. So, the next example I chose was 2x to the power of 5 plus x4y plus y to the 5 equals 36. You can tell that it is quite difficult to solve for y in this equation or express it in explicit form. So we have no way but differentiate it implicitly. So this is what we're going to do. So we know that we have to take the derivative of every term. d dx of x to the power of 4 times y plus d dx of y to the power of 5 equals d dx of 36. Okay, a few interesting things we'll discover here. First of all, this term in here is explicitly differentiated because the variable in the term that you are differentiating is the same as the variable in the derivative. So 5 times 2, 10, x to the power of 4. That's the derivative of this term. Plus, now, in this term in here, we see that we have a product. We have a product of two things, x to the 4 and y, which means we have to apply the product rule here. So here we go. We're going to open up brackets, and we're going to take our time to differentiate patiently. Okay? When we are patient and we know what to expect, we are more focused and we do a better job at whatever we're trying to do. So here we go. We're going to have the derivative of x to the 4, which will multiply the other factor y, and then plus, that's because product rule, right? So the derivative of y times the other factor, x to the power of 4. I'm going to close the brackets in here. So what we just did was differentiate this term here. Okay, now next we have to differentiate y to the power of 5, another implicit differentiation here because we don't have the same variable. So this would equal 5y to the power of 4, just power rule, and then multiply by the derivative of inside dy dx equals, the derivative of a constant is 0. Now, right now, what we just did was differentiate that blue highlighted term, okay? And let's give a color to the first term, why not? Here we go. So, remember what our variable is here. So, our variable is dy dx. So let's take a look at where we see dy dx in here. Let's spot dy dx. So we have dy dx in here. And we have dy dx in here. So we're going to keep an eye on it for now. In the meantime, we'll continue with simplifying. So 10x to the power of 4. And then plus d dx of x to the power of 4 is 4x to the power of 3. Plus, and this term here, I'm going to write it as x to the 4 dy dx. So I'll write x to the 4 first, so I won't have to use too many brackets. Because if it is after it, you don't want to write x to the 4 because you don't know, without brackets, you won't know if they're connected to each other. And then plus 5y to the power of 4 dy dx. Again, I'm going to keep an eye on my variable here, okay? So my variable is dy dx. We have to solve for dy dx, which means we have to isolate it. Now, dy dx is in these two terms. Okay, one in here, one in here. So these two terms will stay on the left side of the equation. And we'll have here x to the 4 dy dx plus 5y to the power of 4 dy dx. The other terms, 10x to the 4 and 4x to the power 3, will be transferred to the other side. So negative 10x to the 4 plus minus 4x to the 3. So now we're going to keep an eye again on our variable, and in order to solve for dy dx, remember that these are not like terms, because you can look at x to the 4 and 5y to the power of 4 as their coefficients. They're not like terms, right? So we're going to solve by factoring out dy dx. So x to the 4 plus 5y to the power 4 equals negative 10x4 minus 4x power of 3. So in order to solve for dy dx, we are dividing both sides by x to the 4 plus 5y to the 4. So this will leave us with dy dx on one side equals negative 10x to the power of 4 minus 4x to the power of 3 over x power 4 plus 5y to the power of 4. Now remember what our task is in here. We want to find the slope of the tangent later at point 1 and 2. And we have just found the derivative, or we just differentiated it. So we'll say that the slope of the tangent would equal the derivative dy dx evaluated at x equals 1, y equals 2. So that would equal negative 10, x is 1, so 1 to the power 4, minus 4, x is 1, so 1 to the power of 3, over x to the 4, which is 1 to the power 4, plus 5y, which is 2 to the power of 4. Let's evaluate. So that would be negative 10 minus 4 over 1 plus 2 to the power 4 is 16, and 16 times 5 is 80. Negative 14 over 81. So this would be the slope of the tangent. Okay, and we're done. So in order to reinforce our understanding of implicit differentiation, I brought in a couple more examples. So I encourage you to try this on your own. I will continue differentiating here. Notice that we have a bunch of terms in here, so be very cautious. And what we have here is, sorry, I'm going to make one, this is a typo actually. So we'll start with d dx, 5x to the power of 3, plus d dx of xy squared equals d dx of 5x cubed y cubed. Okay, so let's get started. So here we have implicit. So that means we have 15x squared plus. Now notice that here we have product rule, which means that we have the derivative of the first term or the first factor multiplying the second factor, which is y squared, and then plus the derivative of the second factor, which is 2y dy dx, and that multiplied by x, which is the first factor. And we'll close this down. So notice again that here we just differentiated this one term, this one product. In the same way, we'll continue with the other side. So on the other side, we'll have d dx of 5x to the power of 3 times the other factor, y to the power 3, and then plus, so remember that again we have product rule, right? Plus the derivative of y to the power 3, which will be d dx of y, and then we have the outside function 3y squared, and then times 5x to the power of 3. Okay, so again, product rule. So this would be just the derivative of the term on the right side. So let's continue simplifying. We need to solve for dy dx. So let's put dy dx in here. So we have a dy dx on the left side, in this term. And we have a dy dx on this term here. So which means that these will be the two terms we have to eventually bring to one side, okay? Because they will carry the dy dx are unknown. So I will rewrite this expression in a neater form. So we have 15x to the power of 2 plus, now the derivative of x in terms of x is 1. So this is 1 multiplying y squared. So that's just y squared. Plus, we have 2y dy dx times x. As you can see here, 2y can join x, so 2xy. And then dy dx equals, so the derivative of 5x to the power of 3, that's explicit differentiation, 15x squared, multiplied by y to the power of 3, so y3. And then plus, here as you can see, we have 3y squared, we have dy dx, and 5x cubed, all multiplying each other. So 3y squared and 5x to the power of 3 can multiply and join each other to become 15x power 3 y squared, and then dy dx. Okay, so notice that our variable, or the unknown, is in these two terms. So these are the two terms we'll bring to one side of the equation. So we're going to leave 2xy dy dx on the left side, and we will have this term join the dy dx term on the left. So that would be minus 15x cubed y squared dy dx. The rest of the terms will go all on the right side of the equation. So 15x cubed, x squared y cubed is already on the right side. We'll have 15x squared and y squared move to the other side, and they will become negative, obviously, here. And now we will have to factor dy dx so that we can prepare dy dx to isolate it. So we'll say then we have dy dx. Oops. Two xy minus 15x cubed y squared equals 15x squared y cubed minus 15x squared minus y squared. To solve for dy dx, we'll divide both sides of the equation by the coefficient of it, which is this funny looking expression. So 2xy minus 15x cubed y squared. So this would be dy dx. That's it, the answer. All right, last example. We have x squared equals 4x squared y cubed plus 1 to the power of 2. So, same idea. D dx of x squared equals d dx of, careful here because we have a chain, so you see you have a power of 2, 4x squared y cubed plus 1 all to the power of 2. So this is my favorite term here, my only favorite, because that's explicit differentiation. It takes no time to differentiate. That's 2x. Here we have a little bit of work to do. So first, we have to pay attention to this power, the outside function. So we have a chain and implicit here. So that will give us 2. Whatever is inside the brackets, 1 power less than 2, which is power of 1. The expression inside won't change. And now we have to differentiate the inside, which is 4x squared y cubed plus 1. So here we go again. We have 2x equals, and you can see actually that we have a coefficient of 2 on both sides. So this 2 and this 2, we can simplify them, right? Because here is a multiplication, right? Like throughout the right side, this is a multiplication of terms, so that means that 2 is a factor, right? So we can write this as x equals. So this first group of terms must be kept in brackets because it's a binomial. You have 2 things in here, right? And now we have to differentiate the first term, 4x squared y cubed, and plus 1. Now remember that the derivative of the sum equals the sum of the derivatives, so that's d dx of number 1. Okay, so notice that here we have a plus 1, and that's why we have the 2 derivatives split up. X equals, keep this in brackets still, 4x squared y plus 1. And now here we're going to have a little bit of work to do because we have a product rule. So we have a product. which means that we need to open big brackets here. And we'll have d dx of 4x squared multiplying y to the power of 3. And then plus, I'm going to change the color of it to indicate that these are together, plus product rule, right? So we have d dx of y to the power of 3 multiplied by 4x squared, the other factor. And then we have to add the derivative of 1. Derivative of 1 is 0, so we don't have to do anything in here. So I will actually make the brackets a little bit more pronounced in here, like in purple, just to indicate that these are the super big brackets, so the outside brackets here, okay? And we have a multiplication of these two main things. We have a little bit of work to do here, obviously, but we're not afraid of work. So here we go. 4x squared y plus 1, big brackets. Derivative of 4x squared, remember this is explicit, that's 8x times y to the power of 3. So 8x y3. And then plus, now the derivative of y cubed, that's implicit, 3y squared dy dx, and then times 4x squared. Okay, so I'm going to take a little bit of space here. So we have x on the left side equals 4x squared y plus 1 and 8x y cubed. I will simply rewrite this because I want to have it in one place, plus 3y squared. Actually, these 3y squared and 4x squared will combine. Let's combine them, it's better this way, to make 12x squared y squared, and then dy dx. Okay, so one second, I just want to make this a square bracket to indicate they are together here. Okay, now let's plot our variable. Where is our variable here? The variable is dy dx right here. That's the one we want to solve for, and it's inside this factor. So in order to isolate it, we first need to divide both sides by the coefficient or the other factor of the purple bracket. So 4x squared y plus 1. 4x squared y plus 1. So that will give us 8x y cubed plus 12x squared y squared dy dx equals x divided by 4x squared y plus 1. Now again, remember that our term or our variable, or the term that carries our variable, is right here. Okay, so that's the one we want to isolate, which means that 8xy cubed can move to the other side. So we'll have 12x squared y squared dy dx equals x divided by 4x squared y plus 1 minus 8xy cubed. And now we'll divide both sides of the equation by 12x squared y squared, which means that this term here is multiplied by 12x squared y squared, I mean the denominator. And the same thing applies to the other term. Let me make this a little bigger so that we can organize our work better. Okay, so if we divide by 12x squared y squared, that means we are dividing both terms, or every term in the equation. So we have 12x squared y squared in here and 12x squared y squared in here. So we can simplify, and what we have here is the x, and one of the powers here will reduce. So we have 1 over (12x y squared) times 4x squared y plus 1 minus 8 and 12 can reduce to 2 over 3. We have a power x to the power of 1 and x to the power 2 in the denominator, so x to the 1. So one of the powers of x in the denominator will reduce this power. And y to the 3 over y to the 2 is simply y. Obviously, we don't have to write the power of x to make the answer look a little bit prettier than we are going to write it as 3x, okay? So that would be the value of dy dx, or the derivative, I should say. There is no value to this as of yet. Okay, so we differentiated quite a complicated implicit equation. And I know that I said last example, I promise, but here is another one that you can try on your own. I will do the last one. And but really try this on your own first. It's not as complicated as the previous question. And we have d dx again, x squared, plus d dx. Remember, we say powers for radicals. So y to the power 1 over 2 is d dx of x squared y cubed plus d dx of 5. So remember that here we have a product. We got to take care of that. And here we have implicit. The rest are the easy terms. So we have 2x, that's explicit, plus half of y, and then y to the power of 1 over 2 minus 1. Don't forget dy dx equals, and now we have product. So that would be the derivative of the first factor, x squared, multiplied by the second factor, y to the power of 3. And then plus the derivative of y cubed multiplied by the other factor, x squared. So done with this product rule here. Okay, and plus the dx of 5, which is 0. All right, so here we go. We are simplifying now. So 2x plus 1 over 2 y to the power of negative 1 over 2 dy dx equals, here you have explicit 2x times y to the power of 3 plus, here we have implicit 3y squared dy dx, and then times x squared, so the product of these three things. Now let's plot our variable. So the unknown is dy dx, and is located in these two groups of terms. So we have one dy dx term on the left, one dy dx term on the right, and we'll group them to one side of the equation. So we have 1 over 2, and I'll write y to the power of 1 over 2 with positive exponents here, dy dx. We'll allow this term to join the left side, so that would be 3y squared x squared, or even better, 3x squared y squared. Obviously, it's going to be minus because it's plus and it's moving to the other side, and dy dx. And that equals 2x y cubed. That's already on the right side. It's not changing. And the last term, which is 2x coming from the left side, which means becomes negative 2x. We'll factor the dy dx term. So we'll have dy dx equals you can either solve right away or you can see what the factor is in here. So 1 over 2 y to the power of 1 over 2 minus 3x squared y squared equals 2x y cubed minus 2x. Another thing we can do in this case is bring these two terms together. So we'll have dy dx, and then 1 minus 3x squared y squared times 2y to the power of 1 over 2, everything 2y to the power of 1 over 2, 2xy cubed minus 2x. A little bit more simplifying for the factor of dy dx. So this would be 1 minus 6 x to the power 2, y to the power of 2.5. So we're adding the powers of 2.5, which is 5 over 2, all divided by 2y to the power of a half, equals 2xy cubed minus 2x. And now we're ready to solve for dy dx. We'll say that would equal 2xy cubed minus 2x multiplied by the reciprocal of this coefficient here, or this factor, which is 2y to the power of a half over 1 minus 6x squared y to the power of 5 over 2. And this would be the final answer for the derivative of this quite interesting implicit equation. So I hope that all the explanations made sense, and I hope that you enjoyed learning about implicit equations.